thanks so much for joining us tonight. My name is Barry Erickson, and I'm Community Engagement Coordinator here at Wheaton Public Library. Tonight, we are proud to bring you this program on the science of snow. Tom Liberto is a climate scientist and public affairs specialist in the National Oceanic and Atmospheric Administration's Office of Communications, and the star and creator of NOAA's first ever cartoon series, Teek and Tom Explore Planet Earth. In addition to his work at NOAA, Tom served as the lead for the Department of State's U.S. Center at the United Nations Climate Change Conference, COP29. He previously served as emcee at the U.S. Center of COP21, where the Paris Agreement was forged. As lead and emcee, Tom organized, planned, and ran the U.S. Center, the U.S. government's public outreach space, during the negotiations. So we're just delighted to have you with us tonight. Tom, thanks so much for spending this evening with us.
Yeah, thanks so much for having me. Let's talk about snow. My background, I'm a climate scientist now, but I got into this field as a big old weather nerd. And I've loved the weather since I was a little kid. Specifically, I've loved the snow since I was a little kid. That's me. I'm the little guy on the left. That's when I was 4 years old in a snowstorm. I grew up on Long Island, so I dreamed of snow and nor'easters every single year. This was a good year for it. I'm the youngest of three boys. I got lots of snowballs thrown my way. But I've loved the weather since I was a little kid. In third grade, I said I wanted to be a meteorologist when I grew up. And I kind of got into the field and I kind of got more interested in climate and I've been interested in communications. And I've been able to meld those two worlds together. But my first love and my deep love is always on snow. And I always say when you meet a meteorologist, someone interested in weather, you think we love all weather equally. That's not true. We all tend to have certain aspects of the weather we like more. So like I'm a snow guy. There's tornado guys and gals. There's hurricane people. There's all sorts. I'm sure there's a sunny day person out there too. So if you ever meet a meteorologist, ask what type of meteorologist are they? What do they actually like? And a sneak peek, actually, if people come around, they wait to the weekend to see Twisters. It's cool. It involves the National Weather Service, which is inside NOAA. And one thing to know about the movie that they did for dramatic effect is that they made the weather forecast office in New York City located in Manhattan. And I'm here to tell you, as someone who grew up on Long Island outside New York City, that is absolutely not true. The Weather Service office is actually out in Upton on Brookhaven National Lab, about 45 miles out onto Long Island. Another fun fact, though, the Weather Service office in New York City used to be in the basement of Rockefeller Center until I imagine rent got too high and they moved out onto Long Island. But let's talk about snow and snowflakes. This is beauty. This is art. This is natural art. Like the fact that physics in our atmosphere can create something as beautiful as this is kind of mind-boggling. Now, you might be thinking, how the heck did this actually fall from the sky? You'd be right. This is actually created in a lab. You can actually buy prints of these things, but these are fundamentally how snowflakes could form without mucking things up in the atmosphere, with the things being more chaotic. You just perfectly create a snow crystal in a lab. Now, these actually were all taken from nature. They're basically fell down on a plate, and we're able to be looking at them with microscopes and take photos. These are natural. These came out of a snowstorm that came across Long Island about 10 years ago. And you can see just how different they all look, but they're all similar in some shape. They have these six sides, right? Although they might manifest themselves in different ways. And it's kind of amazing that we have this sort of variety when it comes to snowflakes falling from the sky. So I'm going to break down this talk in two different things about snow. Snowflakes, how they form, and then I'm going to get into storms and what types of storms tend to affect the United States, especially areas around Chicago, but across the Great Lakes and into the Northeast as well. I'm talking to you right now from Washington, D.C., where we saw about 7 to 8 inches of snow earlier this week. On Monday, my kids have been off of school for 2 days for 8 inches of snow, which would have been mind-boggling to me as a kid growing up on Long Island. In fact, they have closed schools tomorrow, 3 days for 8 inches of snow. I went to college in upstate New York, and we would have 24 inches of snow, and they would just tell us to walk carefully to class. So my kids don't know how good they have it. So these are also plates, a little bit more rusty plates looking at snow across. This is actually taken on Long Island. Dr. Brian Coley, who was my advisor way back when I was in grad school. Again, some really amazing shots just taken out of a snowstorm. And you can see this beautiful sort of image. Now, we saw all the variety that we saw earlier. You might be thinking, what controls that? And I show you this graph. This is basically showing that what determines the way a snow crystal forms depends on the temperature, but more importantly, what we call saturation, how much moisture is in the atmosphere. And when you change these sorts of numbers, temperature and saturation, you can get different sorts of crystal shapes when it comes to snow. And this is one of the reasons I'm going to hark on this a lot, why we always say no two snowflakes are alike. Well, a snowflake, as it's falling through the cloud, is going to be interacting with different levels of moisture and temperature, microscopically changing, that no other snowflake is going to be taking the exact same path. And as it moves from, let's say, a plate shape, that middle shape, it can move into a column. It can move back into a solid plate. It can move into like the feathery look on the very top. And that can all manifest itself on the snow crystal as it's falling through the cloud. So just these small changes, and as it flutters down, no two snowflakes are going to flutter the exact same way. So you're going to see all slightly different snowflakes as they fall to the ground. And this kind of image is a very scientifically way of saying things can be crazy up in the atmosphere. Now, what is our atmosphere made up of? This may seem like a simple question. It's water, when we talk about what a cloud's made up of, but it's solid, liquid, and gas. All three states exist at the same time in the clouds we're talking about here. So we have solid. We're talking about there could be ice crystals depending on how tall the cloud is. When we have a snowstorm, obviously there's some solid solid water in there. Liquid. A cloud is cloud droplets. Cloud droplets are liquid water droplets. And then gas, we have water vapor in the air. And it's the interplay between the gas molecules, between the liquid droplet and the solid ice crystal that lead to there being growth of snow crystals and ice crystals in clouds. So again, we have a cloud. Clouds form as air rises. As air rises in the atmosphere, it cools down, and it basically leads to the water vapor condensing into liquid water. And we have all those cloud condensation nuclei, and that exists within a cloud. But within a cloud, depending on the temperatures, you can have a mix of ice crystals and water droplets all happening at the exact same time. Now, I want to make a note here. When we say cloud droplet, we're not talking rain droplet. A cloud droplet is itty bitty, and a small rain droplet is over 2 times the size. That's the scale is much different. This is kind of blowing out of proportion, but it's much different. A cloud droplet's not going to be falling to the sky, falling to the ground. A small rain droplet will have enough weight behind it to have gravity affect it and move down to the surface. So, how do we create ice crystals? Well, ice crystals don't just form willy-nilly. They need something to form on, similar to how water droplets form too. Water droplets don't just form. A water droplet forms on what's called a cloud droplet forms on what's called a cloud condensation nuclei. It could be something as like sea salt. It could be dust. It could be a lot of different things in the atmosphere. Same thing with ice. Ice needs to form on some sort of nuclei, and then what we call supercooled water can hit that nuclei and form an ice crystal. Now, what's super cool water? That's liquid water. It's not like, oh, the cool kid in school, we call it super cool. It basically is referring to water, liquid water, that is below the freezing point, but has not turned into solid state, that exists in the atmosphere because it doesn't have something to freeze onto. It doesn't just manifestly freeze like that. You need temperatures about negative 40 degrees Celsius or so for liquid water droplets that are super cooled to form into crystals immediately, like just snap your fingers. Usually they need to have something to form onto, which is that nuclei. And nuclei aren't many, at least ice nuclei aren't many in a cloud. So we have these two things existing within a cloud. We have the ice crystal, your future snowflake, and we have your super cooled liquid water droplet. And now in the atmosphere, we often talk about high pressures and low pressures, right? Air blows from a high pressure to a low pressure because it's trying to make everything equal. It doesn't want the low pressure to be low. It wants it to be medium. The high pressure is too high. We want it to be medium. So it moves from high to low. Something similar happens in a cloud. So all those molecules, those are gas molecules, water vapor molecules that are around the liquid water and around the ice. Now, which one do you think it's easier to go from, right? It's easier for a liquid water droplet to turn into gas than it is for a solid water droplet to turn into gas. So that means there's much more interplay going on between, which means there has to be, if it's an equilibrium, I mean, the amount of liquid gas turning into liquid water equals the amount of liquid water turning into gas, you need to have more molecules around it, which increases the pressure around the liquid water. It's a bit harder for ice. So the pressure around that is actually less. So we have high pressure and low pressure. And what happens? Well, the molecules be like, you know what? We got to help out that low pressure. And they help move over to your ice crystal and they make it bigger at the expense of your liquid water droplet. And eventually now the liquid water droplet got smaller. So it needs to basically release more. And his process happens over and over again until eventually, pop, there goes the liquid water droplet. And we have a big enough snowflake. And once it gets big enough, it can start to fall down. And as it interacts, it can run into other water droplets, which can instantly freeze on it to make it rind. It can lead to there being more water vapor being deposited onto the snow crystal, leading it to grow and design itself in different ways, depending on the temperature that the snowflake is falling into. So all of these things are happening to have one of those snowflakes fall to the ground that you catch on your tongue. And oftentimes the big ones that you catch on your tongue are like kind of conglomerates that basically can be sticky. So they can touch each other and kind of fall in clumps, which leads to them falling faster. This process that I just mentioned is called the Bergeron-Findeisen process. But it's also was created or came up with by a man named Alfred Wegener. And this, if you ever want to feel like you did not succeed in as much as you did in life, this man, Alfred Wegener, not only came up with Bergeron and Findeisen, this idea of how ice crystals grow in clouds, but this is also the man who came up with plate tectonics, a process that people thought was completely wrong when he came out with it in the early 1920s. That was proven in the 1950s when there was drilling and geologic work along the mid-ocean ridges in the ocean. So this one guy came up with two revolutionary ways of understanding how our planet works, as if he's like, you know what, the Earth is one thing, let me figure out this major thing with the atmosphere as well. I've never felt less of a person when you're talking about that. It's unbelievable this guy was involved in both of these things. So back to this. So you can see how now, depending on how things fall and the environment they interact with, you can have different sorts of snowflakes. And you can lead to these. These are what they look like in real life. Hollow columns. Might be weird to think about that. Ice needles. You have these stellar crystal sector plates. And if you've never experienced needles falling from the sky, it is weird. It happens in a very specific temperature, so it doesn't happen that often, but you can have storms depending on the environment where you can have just a bunch of like needles fall. And you can see here, depending on what type of flake is falling predominantly, it can lead to there being differences in the accumulations. It's a lot harder to accumulate snow with ice needles than it is with your more classic shapes of snow. And again, here are just some of what these look like. That is a plate and a columnar combined on the upper left. And then you have this rimed snowflake. It's a snowflake that was falling and then liquid water kind of froze on it like little ice blotches all over it. It's kind of amazing how many things can happen in our atmosphere. So why is the snow white? We get that question a lot. Well, it reflects all the sunlight. So you're basically seeing it as white. Let's not talk about the yellow snow at this point. It's a quick question. And you can see how beautiful this can make it look across the planet. I should have grabbed this for yesterday, and you could probably see this giant swath across the middle part of the country from where the snow fell, from the plains all the way to the East Coast. But it shows up so unbelievably well on satellites, as well as for ice cover as well. But let's talk about storms now. One, an Alberta Clipper. Now, you all in Chicago might be experiencing an Alberta Clipper, I believe, on this Friday or Saturday, end of this weekend. Alberta Clippers are these kind of quick-moving storms. They're weak storms. They form in Alberta. They're not really close to major water sources, so it's not like they're super wet, but they move pretty quick. They jot across the United States, and they leave kind of like what I like to call conversational snow. It's not necessarily going to shut down schools for a bajillion years, especially in areas that are used to snow. It makes things pretty. And it's a quick blast of like 3 to 4 inches of snow in general. That's a kind of classic Alberta Clipper. They move quick, drop a little bit, make things pretty, and they get out of there. But then you also have things called a nor'easter. A nor'easter is basically what they call for northeast winds across the East Coast, because as you have that counterclockwise flow of the winds, you have that coming down across the Northeast as it's coming up, and it hugs the coast. It hugs the Gulf Stream with that warm water, giving it a lot of energy, and it leads to this mix of rain, snow, and both at the same time. And depending on exactly where that storm tracks, leads to what happens when it comes to where we see that rain snow line across the East Coast. These are your big ones. These are your blizzards across the East Coast. These are the ones that drop 20 to 30 inches of snow for the Northeast. But you don't have to actually have them just across the coastal areas. You can actually have these form inner and outer, depending on. I can show you some of those paths a little bit. And you can see here that rain snow line almost always follows the I-95 corridor. And that's not because that has a thing against traffic. It's just the I-95 corridor, if you look at it on a geographic map, is actually part of where the coastal plain changes into the Appalachian Plateau, the mountains. So you have that. That's basically where the I-95 is. So there's a geographic sort of region where that's where the coastal zone kind of is and ends, which is roughly around that point where the warmer air from the influenced by the ocean can impact that. So depending if the storm is just far enough to the east, to get to the east, you can have that all be snow, or 50 miles to the west, and you're stuck on the rain side, which makes forecasting these a big old pain with that rain snow line. And again, a lot of this happens when we have a curvy or bendy jet stream. And jet stream basically is that border between cold air to the north and warm air to the south. It's really high in the atmosphere, but it really is reflecting the state of the atmosphere entirely. So when you have these big dips south, it brings a lot of cold air to the south and warm air to the north. Cold air brings warm air to the north, and that fuels a temperature gradient, helps to fuel storms as they go up there. But depending on where that is, it doesn't have to be across the East Coast. It could be just, let's say, 500 miles to the west, and it can lead to there being major impacts in other places. So this is an old image, but it's an oldie but a goodie when it comes to just tracks of the types of storms that you tend to see across the United States. You're looking at number 2 and number 4 for Chicago and the general Great Lakes areas if you like snowstorms. 2 is, again, they both kind of form middle part of the country on the other side of the Rocky Mountains. They can kind of pick up moisture from the Gulf of Mexico and then shove themselves straight up. And you can basically see there being this interaction between Arctic air from the north and this warm air from the south, fueled by the Gulf of Mexico and the Atlantic Ocean, and it can lead to there being all sorts of snow fireworks across places in the Great Lakes to the East Coast, depending on just where all these things tend to set up. Now, within a snowstorm, we also can have, you can see always like there's some places get what we call jackpots within a winter storm, because they're stuck under what's called a snowband. Now, snowband is within a storm itself. You can have areas where the wind is actually hitting each other, converging even more so. And you can basically see this snowband of elevated snowfall rates just kind of sit there. And as the storm is moving, it can end up like moving up and then out. And when it does that, it leaves basically a pivot area where one area is moving like this, and then it moves like this, and it goes like that. So you have some place that within the snowband can get stuck under it for 6 hours with 3-inch-an-hour rates. And those are the areas that you can see have a tremendous amount. This is a very famous snowband across New York. Not only because I grew up there, this is from 2006. This snowband dropped like 30 inches of snow in places across the northern Bronx and into just north of New York City. It just sat there as the storm pivoted itself out. So within a storm, even then, when we give these broad forecasts for like, oh, it's going to be 12 to 24 inches, we know that someplace within that is going to see the snowband when these really, really strong storms that could see those elevated amounts. I've mentioned I've talked for a while now, and I talk very fast, I apologize. But one thing I haven't brought up yet is blizzard. You might be thinking, what's a blizzard then? Why haven't I brought up blizzard? I'm talking about snowstorms. Aren't these blizzards? Well, a blizzard has a very, very specific definition. And if you can believe me, a blizzard, one definition of a blizzard in this definition, it does not involve falling snow. You can have a blizzard with no snow falling from the sky. A blizzard is talking about how strong the winds are, how long these conditions are occurring, and the visibility. Basically, you can't see your hand in front of your face. Scientifically speaking, there's about 1/4 of a mile visibility. And then just that snow exists. Snow is what's causing the lack of visibility. So that's what it takes to have a blizzard. Um, and when I say snow exists, and this happens a lot in the Great Plains where things are very, very flat, you can have a snowstorm happen, and then the next day, really, really strong winds pick up and they blow that snow around and you lose visibility. You can have blizzard conditions just from blowing snow on the ground. Now, most of the time we talk about blizzards, it's with falling snow, but you can have what called ground blizzards from the plains when all this really, really soft, fluffy snow can get blown up into the air and you can't see anything. And that can happen in and of itself. But so a blizzard does actually mean like, oh, this much snow has fallen or this much snow is falling. It all has to do about the wind and your visibility and how long those conditions last. That's what it takes to get a blizzard. So you can have a blizzard with 12 inches of snow. You can have a blizzard with 24 inches of snow. It depends on the type of storm. It'd be harder with 12 because you'd figure if you have the winds that strong, it's probably a good snowstorm. But that necessarily blizzard in terms of definition, you don't have to be that exactly. And then something which is really close to my heart, it's lake effect snow. I didn't bring it up on any of the things that the storm passed either. This basically happens when cold air blows over warm waters of the lakes, relatively warm waters. It picks up moisture and then deposits that on the windward side of the lakes. And you can see these can be 140 miles long at times, and these things can be incredible. This is from 2014. This is one of the epic ones that dropped like 4 feet, 5 feet of snow just south of Buffalo. You can have these across every single one of the Great Lakes. Buffalo is a classic one just because Lake Erie is almost perfectly designed to just have winds flow across it like this. And to put this into perspective, this is what it looked like. And this is how narrow this band was. You're in downtown Buffalo looking to the south, and you can see a behemoth of a snow band, and you basically are fine. You're not getting any snow. But underneath that band, you're looking at 4, 5, 6 inch an hour rates from these sort of these effects. This often happens during Arctic blasts early into the winter time. And the reason I say early is because once the lakes ice over, if they do, it kind of shuts off the lake effect snow season. So early December into January, you tend to see these sorts of events. You can even see them later into the spring if you have an Arctic blast into the spring after the snow and ice has melted in a lot of the Great Lakes. And you can see here across in Michigan and other areas, you can see basically large areas seeing this snow during that same period of time. So it's not just one lake, it's pretty much all the lakes can see it. But it wouldn't be, I'd be remiss if I didn't talk about what's happening now, the forecast happening now, and we'll talk about climate and climate change as well, because the fastest warming season across the United States is winter. The fastest warming season for the Northeast and the Great Lakes is winter. And currently, we've seen one of the warmest years on record for the United States. And this is what the 30-day mean anomaly temperature has been through yesterday. And it's been pretty much warm everywhere across the country. And this could have a bunch of impacts too. This is looking specifically now into Great Lakes and Chicago and Illinois and all those good places, warmer than average. And this is what we've seen for snowfall this season as well. So just because you have, let's say, an above average precipitation year in the winter does not mean it's going to mean snow. If the temperatures get warmer, that can really hammer and knock down that. Just also, it means if you're in a snow drought, it doesn't mean that you're in a water drought. You can have a snow drought just because more of that snow is falling as rain. And that is certainly a bigger issue in a lot of places where we've seen those sorts of things so far. And you can see here, looking back at the last month or so, precipitation has been around average, maybe a little bit below average. It's not remarkably so, I would say, in either directions. Maybe when you get to the eastern side of Michigan into Indiana and Ohio, it's been above average and whatnot. But if you take a look on the right, that is the snowfall percent of mean, and that has been below average. And this kind of goes to hint that even though you get the precipitation, it's been falling more as rain than it has as snow, tied to those warmer temperatures. And that is a broader story. It's going to be happening for, if you're a snow fan, for a lot of the places in the northern tier of the country, as temperatures warm, is that you'll see more rain as opposed to snow. Not to say you won't see snow, you will still see snow for the foreseeable future, even if it might be harder to do so. It just means that overall, taking a look at entire seasons, you'll see some of those trends start to emerge. One other sort of thing that we look at too, we can have these indices that we create that look at how severe a winter has been so far. Here, you're looking at the bluer it is, the purple it is. Those are severe winters. Blue, think snow. You can see, generally speaking, for much of the country, It's been a pretty mild winter so far. We're only a month in. We have plenty of time for things to get all crazy if they want to get crazy. But you can certainly see here that mainly just due to the last storm, some places in the central and eastern parts of the country have now been around average. But in general, it's hard to find too many moderate to too many severe winters so far. And one thing we also look at here with those warmer temperatures is also taking a look at that ice cover across the Great Lakes. And right now it is still well below average, although we saw a big spurt in the last couple of days. I would expect this to increase over the next week or so as it stays pretty cold. Temperatures are not going to approach freezing probably until the weekend, if that. So it is going to be a cold time. I would not expect to see this number jump up in the next week or so. We just want to take a look at what it looks like, spatially speaking. This is where all the ice is across the Great Lakes. Now, usually like Erie tends to freeze over. It has not yet. That's been a consistent thing the last several years or so. Last year was ridiculous in terms of how late it was when the ice actually started to freeze a little bit. But we're still also seeing much of the lakes pretty much being open, which means that lake effect snow season is still on for many of the areas in the Great Lakes. And we take a look at the forecast now, because that's what everyone's always interested in. I already kind of gave you the weather forecast. It's going to be cold and then might get some snow this weekend. And if you take a look at the monthly outlooks for the rest of January, generally speaking, it's tilting out towards being cooler than average. A lot of that's basically from the first 2 weeks of the month expected to be pretty below average, which can have a big impact on what the month looks like. And precipitation, it's kind of up in the air. We don't exactly really know. We're currently potentially going to enter into a La Nina, which tends to lead to there being below average precipitation across the southern tier of the United States and maybe a bit of above average when you get closer to the Great Lakes or so, which can then depend on what the storm types could be when that happens. But in general, the signal is too hard on a monthly timescale. So a little bit of a difficult thing to say if you're interested in snow. It's not a bad forecast, I would say, compared to years past. Usually temperature has been well above average. So below average temperatures is, the key component for a lot of things for even snow to be possible. And I'll end this with climate change, and I'll happy to answer any questions. If ever there's any questions, I'll talk about weather, climate, whatever the heck you want to talk about when it comes to any of this stuff. Interestingly enough, lake effect snow might increase for a time due to warming temperatures in our atmosphere. Why? Because the ice season on the Great Lakes might remain ice-free for longer, which leads to there being more potential for lake effect snow. So as long as temperatures can stay cold enough, you could see lake effect snow increase as the ice decreases across the Great Lakes. We've seen snow cover decrease across the Northern Hemisphere. The snow depth is generally decreased across the Northern Hemisphere. As you can expect, snowfall amounts decrease, even if precipitation totals might increase, which they are expected to in a lot of places in the Great Lakes and Northeast. And basically, a lot of that is also you're shrinking the winter season, the time when you can have potential snowfall. So that makes it more difficult, and that's necessarily why you expect to see below average precipitation and below average snowfall amounts, with climate change happening. And here's just to take a look at spring snow cover across the Northern Hemisphere as well, which could have an impact on river estuaries and other river ecosystems as well. Less snow cover leads to being less snow melt, which can lead to there being low river levels in a lot of different places. But we can also see there being a clear trend on it being a low snow cover in the springtime, also indicating that shortening of the winter season. And the spring thaw is happening earlier. This is a big image. Those purple areas, what we're really looking at, those are how many days earlier that basically the spring thaw happens. Think of it like when winter really ends, and you can see across parts of those marginal areas. And when you get to the northern tier of the United States, you're looking at 2 to 3 weeks earlier than we've seen happening over the last 50 so years. This is impact. I don't ski. I like the snow tube. I'm a big fan of just enjoying the snow, not going down it too fast. But skiing obviously is a big impact when it comes to climate change as well. And you're seeing a decrease in the ski season length as well for pretty much most places across the country, which is not ideal if you're into that sort of thing. I will stop there, and I can stop sharing the screen, and I'm happy to take any of your questions that you all may have.
Thanks so much, Tom. I'm going to go ahead and remove the spotlight. There we go. Just a reminder to those who are attending tonight, if you have any questions, please go ahead and type those into the Q&A, and I will read those aloud. Our first question was entered a bit ago. Someone asks, can a snow or ice crystal form on another already existing crystal which serves as then the nuclei for the new ice crystal?
Peter, you're exactly right. One of the best ice nuclei is ice. The thing is, you need to get that ice in the first place. But yeah, ice kind of it's a self-feeding process. Once you start having those ice nuclei, they can be like that. Um, yeah, it's a good question. That's exactly how things can form.
Okay. And else is asking how it, this the words might not be quite correct. How does the bringing process?
The Bergeron, probably bet the Bergeron process starts
Okay.
when salt
Start when
touches
salt
snow.
touches the snow. Yeah. How does that work?
Yeah, so it's not like it's not becoming like a salty snowflake. It's just that for whatever reason, some molecules, small molecules, I imagine it deals with the size of them in the atmosphere, basically can just exist to have like something to grab onto. Think of it like a railing, like you're walking down the railing and you just need something to grab onto. So salt is really good because it's the right size and the right distribution. It can sit up in the atmosphere, the salt crystals. Also, that's why dust is just the right size. It can't form unlike a bird. A bird is not a good nuclei, but it has to be like that small size, and salt's just a good example of that. And also, one reason we see a lot of it is because we have those big old oceans, and when the waves are crashing, it can lead to there being salt deposited in the atmosphere. So we tend to see a lot of salt being these nuclei due to that purpose, because it's just kind of right, the right size and the right conditions.
Okay. Thank you. And it looks like there are a couple questions related to snow crystals or flakes having 6 points. And if you can explain why that is.
Yeah, so this is it's always it's interesting. Why six? It's due to the molecular structure of water and how it forms a crystalline shape. And it can only basically because you have those H2O and O is much heavier than the two H's. And when it forms a crystal, it just forms that crystal shape that leads to there being six sides always. It's just how when you turn a liquid gas water liquid into something solid into a crystal, it leads to it forming that shape. It's no different necessarily than why we see crystals in the real life, right? They all have these really particular shapes, and it's because when that substance cools or whatever it is into a crystal, due to its molecular structure of the elements within it, it leads to there being these very specific pathways for how the crystal can grow. And when it comes to water and crystal growth, it's six-sided. So if you see an eight-sided one, I don't know what's going on. We have to figure it out. Call the physics, please.
All right. And this question, I think, is somewhat related. Can you tell us about fractals in snow and ice crystal formation?
I It's a good question in terms of I don't exactly know about that. I don't know if I can answer that particularly well. I'd have to look into that. I apologize.
Okay, no problem. There's a couple questions about snow in Illinois. Someone asked, in the 1950s, Central Illinois would get ice Central Illinois would get ice when we in Northern Illinois would get snow. With climate change, will we be getting more ice storms up north?
It's a good question. So if you just take a look at it physically speaking, right, if you change your climate into something that's more marginal, where you're kind of bordering that freezing line, you would expect there to be more occasions where you see a mix or sleet or ice. The difficulty in determining trends with that is that there just aren't a lot of ice storms. So it's hard for us to say whether there's a trend in ice storms because of climate change or not. There just isn't enough of them to be able to say whether we've seen anything. But just physically speaking, you could see that happening. It's just it's such a rare event. It's hard to be able to say. But the key thing is, yeah, you would expect to see at least something when you're going from temperatures that, let's say, can be more often be in the 20s versus temperatures that are hovering around 32 degrees. You can see those changing sorts of events.
Okay, thank you. Yeah. And someone else says, I've heard that the reason we are having bursts of extra cold weather in Chicago is because climate change is destabilizing the jet stream, allowing cold Arctic air to travel further south. And is this true, your opinion?
This is an incredibly active area of research, and there are folks on both sides of this issues that I respect greatly who come on very different sides of this. So people always ask me, with climate change, I'm a climate scientist, you're so sure about everything, what don't you know, right? And I say, well, I know it's caused by humans and it's warming. But one thing, an active area of research is this question exactly. So the thought is that by reducing sea ice in the Arctic, you're exposing more of the Arctic from ice to water. And that sort of change in the energy can lead to there being impacts further up in the atmosphere, which can lead to the destabilization of the jet stream because the Arctic is warming so much faster, about 4 times faster than 2 to 4 times faster, depending on what year you're looking at, to the mid latitudes. And that can lead to a wavier jet stream. Jet stream becomes wavy, similar to how you look at rivers, right? A strong river is going in a straight line. A strong jet stream is going in a straight line. A weak river is meandering. A weaker jet stream meanders. And when you have a meandering river, you can have a lot of that Arctic air comes to the south. So that is the thought process behind that. Now, on the other side of thing, that scientists, I'm probably more in this camp, is that we just can't tell whether that's actually happening right now. We just can't say. And then also, I wonder if it's kind of the chicken or the egg. What's causing what? Is the warming? I sometimes I feel like it's not necessarily reflecting that sort of processy, or whether we've seen these bigger cold air spurts because of that. So it's still really up in the air, and there are people on kind of both sides are arguing it out, and I'm very curious to see where it all ends up because it's very fascinating. But we don't know. I think it's the best way of saying it right now. It's a scientific shrug of the shoulders.
Yeah, jury's still out.
Mm-hmm.
Okay. Someone else says, I'm from Colorado. Snow and water is a huge deal. What is NOAA forecasting for the next 10 years in Colorado?
So Colorado is an interesting, and pretty much anywhere across the Southwest United States is an interesting question. How do I phrase this? So, no, we don't issue like decadal forecasts, but I can tell you the general trends. The general trends are for a drying out of the Southwest United States. Also, we've seen trends, especially in the mountains, where we've seen the snow line move further up the mountains. We've seen less snowpack over existing over winter, a reduction in the snowpack, which leads to there being fresh water issues. And there's also other issues that lead into water usage, where more folks or more things are using that water. So if you have a dwindling amount of supply, you have an increasing amount of demand that leads to there being a depletion. And that's a broader kind of human story. And also leads to there being water rights issues, which is well above my pay grade. When it comes to states, determining who gets the water. If the water originates, where does it originate? Who controls the river? If you're upriver or downriver, who has rights to that? It's a very thorny prospect and a very hard thing to deal with. One other issue is that when they determined how much water goes to where, they used a period of time where the water levels were higher, just happened to be, and now things have been lower. So now you're kind of dealing with that sort of process. But in general, the thought process is Southwest water is a big issue now, and going to continue to be a big issue throughout the rest of the century and beyond because of climate change and warming temperatures and a lack of snow.
All right, thank you. Someone else asks, can cloud seeding generate snowstorms similar to silver iodide being used to jumpstart rain clouds?
So I don't know if I've ever seen anyone try to cloud seed snowstorms. Now, cloud seeding occurs all the time. You might not realize it occurs a lot of dry areas. And that basically shooting what's called silver iodide, which could be a really good cloud condensation nuclei, which can help to taking advantage of moisture in the atmosphere, creating clouds, and hopefully leading to rain. If you increase the amount of cloud condensation nuclei, you increase the number of cloud nuclei, liquid droplets, you can increase the chance of rain. I would say it's never been proven that it actually works. And the reason why I say that is that it's really hard to say whether that cloud would rain because of that or some other reason that was going on. And a famous example of this is that they cloud seeded a lot right before the Beijing Summer Olympics previously this century, and then it rained. And like, oh my gosh, cloud seeding worked. But the rain happened because of a system that moved across, like a weather system that moved across. It wasn't because of the silver. It's really hard to kind of tease that out. But I've never heard of anyone trying to do it with snowstorms, although I can imagine there's plenty of students out there who would love to try to cloud seed to get more snow so they can get off to school.
Right. It looks like we have just one more question. Someone asks if you would explain again why snow is white.
Sure. So the way when light hits a snowflake or snow crystals on the ground, it scatters and bounces off all of them all over the place and goes in all directions. So because we're basically seeing reflected of all colors of the spectrum, our eyes pick it up as white because it's bouncing on all those ice crystals and all over the place. So we see it all. Compared to when we see light in our atmosphere, lots of things are reflected, but we see the blue more often because of the wavelength. It's the shortest wavelength. And then sunsets are when you have a longer when the sun has a longer time of coming in into the Earth's atmosphere, it has time to reflect more of the longer wavelengths, the reds, the oranges, which is why we tend to see those at sunset. But yeah, just because the light's getting reflected everywhere, and we just see it as white. Although don't look at the snow; it can be very, very bright. You can really hurt your eyes.
Right. Okay. Well, thank you so much for taking the time to talk to us and explain all this about snow and answer our questions as well. Tom, we really appreciate your time. Once this program has been edited and uploaded, we will be sending out a second follow-up email in addition to the resources that I send tonight with the direct link to that recording again so that you can watch it or send it off to a friend. If you would like those resources and didn't get the original email, go ahead and email me at ce@wheatonlibrary.org. That's CE for community engagement at wheatonlibrary.org, and I'd be happy to send those great resources links out to you. But with that, I think we'll say good night. Thank you again, Tom, so much for your time and for providing this program for us. And we hope to see everybody soon. Stay safe and healthy and away from the ice tonight. Thanks. Good night.
Take care, everybody.